Styrofoam is mostly composed of a chemical called polystyrene, and using the power of chemistry it's possible to turn it into my favorite carcinogen called benzene, which is a useful solvent and sometimes reagent, and it's mostly known for giving people cancer. Now, why would someone want to make benzene out of styrofoam? Well, let's say you had a giant block of styrofoam that was about to get tossed into the trash, forming the useless and stupid piece of styrofoam that it. However, what if instead of throwing it out, we chemically recycle it into some cool chemicals and make some cool stuff with it for fun? Anyway, before we start torching the styrofoam, I'm first gonna have to dissolve it in some solvent. Styrofoam is in 99% air, which is trapped by a polymer called polystyrene. So if you dissolve the polymer into solution, then the air is allowed to escape, which will reduce the overall volume that the polystyrene takes up. Toluene is a hydrocarbon and is actually a very small but a notable part of gasoline. And as we all know, styrofoam dissolves in gas very well. In fact, when you dissolve styrofoam in gasoline, it makes napalm. However, calling this napalm would be ridiculous. To prove that it's not a homemade incendiary weapon, which would be illegal, I've lit it on fire and... oh no. For fuck's sake. So I've had to get rid of this as soon as I could, but first I dissolved the rest of the block. Anyway, I've took the totally not napalm outside and put it on a hot plate and cranked up the heating. This makes the toluene evaporate quicker. Anyway, after an hour of heating, we're left with a solid crust of styrofoam, or more accurately polystyrene. This is how the crust looks, and here's me taking my pent-up frustrations out on it. Anyway, I've moved on to more practical methods, like using a hammer to chisel out the pieces of solid polystyrene.
Yeah, I'd say it's like 200 grams. So yeah, it's a pretty good recovery, to be honest. I'm probably about to regret this, but whatever.
Here I'm grinding the polystyrene in my coffee grinder so that it fits into my flask. After I ground everything, I've put it into an Erlenmeyer flask, and then I've assembled the apparatus.
Alright, so this is our cracking polystyrene apparatus. Here's some Teflon tape for sealing. Here's the styrofoam, or at least polystyrene, I guess, so now. Here's the receiving flask. It should be enough for all of the distillate.
So when I was ready, I cranked the heating up to the max, and once we reach a certain temperature, a dense white smoke starts bursting out of the styrofoam pieces. In this reaction, we are thermally decomposing polystyrene into its monomer styrene. However, one problem with this method is that it's inefficient. You can guess that from the fact how styrene is a liquid and you're just getting some nasty white smoke. Eventually, a yellowish liquid comes over, which is a little impure styrene. The stuff in the flask turns blackish, which is also why I'm using some random Erlenmeyer instead of the flasks that I'm actually emotionally attached to. Anyway, I won't be going in depth into this process because I've already done everything here in the first part of this video. I'm just redoing it because I've screwed something up and now I've had to redo it. Eventually there's this black gunk left in the flask, and from this point on the distillate is going to be scarce, so I'm calling the end of this procedure here. In the receiving flask we're left with actually surprisingly pure styrene, and I have no idea why it looks so nice here, but usually it's heavily colored and it kinda stinks. I've had weighed out our yield and it's not that good. I mean, 84 grams is fine and all, but we did just crack 200 grams of polystyrene. Anyway, I've had weighed out 42 grams of styrene for this experiment. In the next step we're going to be oxidizing the styrene molecule into potassium benzoate. So I've had weighed out like 100 grams of potassium permanganate, which is going to be our oxidizer, and I've dissolved it in some water. I tried to stir it with a stir bar, but as it turns out the permanganate has a very bad solubility and all of it is blocking the stir bar from moving. Anyway, I've transferred all the permanganate into a flask and then I've added all the styrene at once. You can immediately see a reaction happen where the color turns from this purplish into a special color that I like to call brown. Anyway, I've plugged the flask with my hand and I have shaken it for dramatic effect. Nah, but for real, styrene doesn't mix with water, so you really have to mix it well if you want the oxidation to work. In this reaction we are using a very powerful oxidizer to oxidize this part of styrene into potassium benzoate. I'm not very sure why the permanganate doesn't shred through the benzoate as well, but I guess that's just organic chemistry for you. You don't ask why something happens, you just kinda accept it. Anyway, even though permanganate is a strong oxidizer, we need to give it a little push in the form of some extra energy. So I started hitting it. And because I was too lazy to set up a proper reflux, I've set up a reflux on a reflux. Eventually I was doing these cycles where I would see if it's hot and then transfer it onto a magnetic stirrer. Anyway, it was late at night, so I've put everything onto a sat bath on low heat and I went to sleep. Next day I've transferred everything in the beaker, and as you can see, there is no more of that characteristic permanganate purple, which means we've successfully oxidized most of the styrene. What's left is the reduced manganese dioxide gunk, which shall be recovered for future experiments. Then the whole thing was filtered through a Bushnell funnel. And even though I'm doing a vacuum filtration, it is taking very long because the manganese dioxide is in the form of these very fine particles, and it's clogging the funnel. Also, I know a lot of experienced chemists watch this content, I guess to have a laugh or something, but if you have any advice for me when it comes to chemistry, then be free to leave a comment in the comment section. Anyway, when I look at the thing from the top, you can see some oil droplets, which is the styrene that wasn't oxidized. After around an hour of filtering, we've got a clear filtrate, and I've added a bunch of concentrated hydrochloric acid into it.
Oh, thank God.
What just happened here is a simple reaction between potassium benzoate and hydrochloric acid, which results in benzoic acid and potassium chloride. Benzoic acid is insoluble in water, so it crashes out of the solution. The whole thing precipitated as these really nice crystals, so I've had no trouble filtering the whole thing. Anyway, I've transferred everything into a beaker, and I've added a highly basic solution of sodium hydroxide. This basically reacts with the benzoic acid to form sodium benzoate. Next, I started evaporating extra water from the sodium benzoate. Eventually, the sodium benzoate precipitated as this fluffy suspension, and over the course of 3 hours, I was doing my best to dry it. Anyway, I've had finally dried it, and I've added around 2 grams of sodium hydroxide into it. And this is the part where we'll be converting the benzoate into benzene. To the ugly flask, which was used to crack the polystyrene, I've added all the sodium hydroxide and sodium benzoate. We are about to start hitting sodium hydroxide in glass, which means the glass will gradually weaken throughout the process or even crack. As I started hitting it with a blowtorch, a mist started being produced, which is either some water which was left in the benzoate or is some byproduct. Then we start getting an actual thick white mist, which is very good, and that means that we're most likely about to start distilling benzene. In the flask you can see the whole thing bubbling, and that's pretty good. In this reaction we are using sodium hydroxide to decarboxylate the sodium benzoate, which leaves us with benzene and sodium carbonate. Because I didn't mix the sodium hydroxide and the benzoate very well, I've had to keep tilting the flask to maximize what yield we would end up with. Anyway, eventually the flask started cracking, so I did a tactical retreat as to not get cancer. Anyway, I guess I was feeling lucky that day, and as I've waited 30 minutes, the flask looked sturdy enough, so I've came back to hitting it. I mean, at that point I should have stopped, but I guess when I saw how much benzene we actually had, I've decided to step my game up. Anyway, at this point there really wasn't that much sense to continuing this. I mean, I'm not that suicidal to wait for it to fully explode, and I guess I did the right call. As when I started disassembling the apparatus, an hour after the reaction the flask just kinda came off. Anyway, I've moved everything in the separatory funnel, and the off-color top layer is the benzene. Anyway, here's our very shitty yield of benzene, however it could have been worse, if I stopped at that moment. I've also got a theory that even though we were using sodium hydroxide, the excessive cracking most likely came from the overall heat, which I was dishing out from the blowtorch. So yeah, this was really stupid, and it's pretty much safe to say that you shouldn't attempt this at home. Or even at all. Anyway, this is all. Thank you very much for watching, see you in the next video.